All right, so this should be the very last segment. We're going to just talk about the two ways to calculate half-life. There's a formula method and there is the table method. I will show you both methods and we'll practice these in class together and you can choose which method you prefer. But basically I said that half-life is the amount of time needed for 1/2 of the original amount of a radioactive isotope to decay. We said all radioactive substances have half-lives. So here you see a graph that has the amount of radioactive isotopes remaining and then the number of half-lives that it's gone through, cycles that it's gone through. So notice you always, you start off at time equal to 0 when no half-lives have occurred. You have 100% of the substance. And then notice after your first half-life cycle, you have a half of it remaining. So 50% would be left. Second half-life cycle, you have 25% left. Then you have 12.5, and then after that you would have 6.25, and so on and so forth. So it's just you keep halving the amount. So the formula method, for that one, you would calculate half-life by using the formula 1 divided by 2 to the nth power times x sub 0, which is your initial amount, equals x sub f, which is your final amount. So let's clarify what each of these stand for. N represents the number of half-life cycles. X sub 0 represents the initial amount of the substance. And then X sub F represents the final amount of the substance. Now sometimes you are simply told your half-life, which is T1/2. So if you're trying to find N, your number of cycles, and you're given the half-life, a little formula you could use for that to find N is N will be equal to the total time that has elapsed divided by the half-life, so the T1/2. Okay? So that's something you might have to kind of use to help you find N for your cycles. Now, some students prefer to use the chart method. If you're not quite as mathy, you might prefer the chart method, and that's fine. Sometimes some problems are better to use the chart method for. Chart method involves just making kind of like a little, I guess I'll call it a T-chart. And in the top column here, in the first column, this is where you're going to put your amount of your substance, how much you started with. And then in the second column, you're going to put the number of cycles or the time that's passed by, whichever you prefer. I like to do the cycles, so N cycles. And what's important to remember here is the very first row for your very, very first amount, you put in the first row, you put the original amount. That's always what goes here. And right beside of it, you always, always, always start with 0 for the N. This means no time has passed by. So this first one here for N is always 0. All right. And so then basically you just keep dividing by 2 over and over and over again for every how many cycles you have. All right. So we are going to be working through these calculations in class tomorrow. All right, the last two things here is fission and fusion. So let's talk about that real briefly so we can focus on the calculations tomorrow in class. Fission was discovered in the late 1930s. The word fission means to split. It's a splitting of the atomic nucleus into fragments. And it occurs inside of nuclear reactors. The word fission means to break apart. Think about it, fizzles apart. It breaks apart. In a fission reaction, you use one neutron, and in return, it generates 3 neutrons. And this is like a chain reaction, like dominoes falling. Once you initiate a fission reaction, just like when you topple over dominoes, one affects the next, and what happens is 1 neutron generates 3, so it exponentially creates more neutrons, 3 each time. Fission occurs in a nuclear reactor, and a huge amount of energy is released in a fission reaction. The next type of nuclear reaction is a fusion reaction. It's exactly the opposite of a fission reaction. Fusion occurs when 2 nuclei or more come together and they make 1 nucleus. In other words, they fuse together to make 1. This occurs on the surface of the sun. So imagine how hot it is on the sun. You need temperatures equal to or greater than 1 times 10 to the 8th Kelvin just to initiate a fusion reaction. So we can't mimic a fusion reaction yet on Earth because we don't have a container as of yet that can actually hold or withstand a reaction at this particular temperature. Finally, I want to end up with, so what are some uses of nuclear chemistry in our world? Well, in a nuclear power plant, they generate electricity with that fission reaction that I mentioned on the previous slide. Also, they can preserve food with the nuclear reaction by exposing, say, for example, this strawberry to gamma rays. It will kill the bacteria, so it would help preserve the food. They use nuclear reactions in medical diagnostic tests like MRIs, and they have radioactive substances that they might do tests for thyroid issues or cancers and things like that. We use nuclear chemotherapy and radiation to kill cancer cells, but the drawback of that is it also harms the healthy cells. So that's the downfall of that. Another use is we can use it to control insect populations and kill mosquitoes and gnats and those pesky little insects that might irritate us. Inside of a smoke detector, there is a radioactive isotope, and so it's used in smoke detectors, and it's also used in radiocarbon dating, also known as fossil dating. So there's all kinds of uses for nuclear chemistry. Now there's also bad uses for that, like for example with nuclear war. Anytime you have something that can generate such amount of power, they can use it in nuclear warheads. And so you have to be very, very careful with radiation and nuclear fission and fusion reactions. Okay, so tomorrow we're going to talk more about this and have some discussion about nuclear reactions and how to balance those nuclear reactions and to carry out our half-life calculations.